So in this next section, we're going to talk about a very famous equation called the Friis transmission formula, which essentially will allow us to connect now the receive and transmit antennas by essentially looking at all the characteristics we've learned and seeing how we can calculate the power that we receive if we know our system and the transmitted power. We're going to make a few interesting assumptions that I have actually listed here to introduce this equation. First assumption is that we're assuming we have free space propagation, so that means that there is nothing else except for my transmitter and receiver. We're assuming that we have line of sight. Essentially, that means that there are no obstacles between the two. There is perfect alignment, so the main beam is pointing from the receiver to the transmitter without any misalignment errors. The antennas are polarized. They're matched in polarization. We haven't really discussed polarization much here, but as you can imagine, the antennas are radiating electric and magnetic field. These are vectors. So some antennas are radiating linear vectors, some antennas are radiating circular polarized fields. And so that means if you're radiating a vertical polarization from the transmitter, you're also well aligned to receive vertical polarization from the receiver. And the antennas are matched, so we don't have any mismatch issues. So if those assumptions are true, which of course can only happen in an ideal system, and we'll see how it changes in real life, then what one can say is that if my antenna the transmitting antenna was an isotropic radiator, then essentially I could easily calculate the power density in free space by taking the total amount of power that I can actually radiate from my antenna and divide it equally on a sphere around the antenna. Now, of course, I don't have an isotropic radiator. What I do have is the antenna that gives me some gain. And so that means that in the direction that my receiver is pointing at, my power is not simply the power that's being transmitted, but the power transmitted times the gain of the antenna. So in that direction that I'm basically radiating, which is the direction right here, I will have the gain to help me in closing the link. Now, let's come to the receiver side. The receiver essentially is going to see that wavefront that is coming to the receiver, and is going to pick a specific amount of power contained in that wavefront. The way we normally imagine this as happening is by looking at the incident power density, which is the one I just wrote down before, and then multiplying this with an effective aperture. It's almost as if the receiver is actually opening an aperture and collecting some amount of this wave inside the receiver. And this aperture is a specific characteristic for every single antenna. And you can prove from electromagnetics, which we won't really do here, that is related to the gain of the receiver, the wavelength lambda divided by 4 pi. So G lambda squared by 4 pi is the effective aperture for every antenna, which basically means if you know its gain, and usually we do know the gain, or at least we can calculate or measure it, you can very quickly find the effective aperture of the antenna. Now, for some antennas, this effective aperture is actually related to the real antenna aperture. For example, if you have a horn antenna, the effective aperture is actually proportional to how big is the actual opening of the horn.